Okay, this is the second part of section 1.2. In this second part, we're still talking about the functions versus relations, domain and range, and graphs of functions. But we're going to need a little tool called interval notation to keep on going, because we're going to be asked to describe the domain and the range of functions soon, and it's very useful to know about interval notation. You might have heard about interval notation. It involves parentheses and brackets. The brackets are used when the value is included. So when you have less than or equal, or bigger than or equal, less than or equal. So when the values are included, you use brackets. When the values are not included, we use parentheses. And that would be strict inequalities, less than, bigger than, not equal. For negative infinity or positive infinity, we always use parentheses. And if you see a little u, that stands for union, and it implies that we're gluing together two intervals. So, for instance, let's look at this first example. I have this is an interval. It's a set of numbers, and let's kind of understand it a little bit better. So let's maybe think about this this set of numbers as in a graphical way. Yeah. So what I have is the values 0, 2, 3, and 5. Yeah? And turns out that so think about what this part means right here. 0 to 2. What that means, it's all the values between 0 and 2, all real numbers between 0 and 2. That includes fractions, decimals, so things like 1.3562, 1.999999815. Those are all values that happen to be between 0 and 2, but not including 0 and not including 2. The fact that 0 and 2 are not included, I'm going to kind of make a little hole right there at 0 and 2 to sort of indicate that 0 itself and 2 are not included, and everything in between them is included. Yeah, and then I have that set together with, so the union with all the values that are between 3 and 5, not including 3 and not including 5. So again, I'm going to make a little space here for 3, a little space for 5. So there we go. And it's all of the values that are between 3 and 5. So things like 4.983. It's very close to 5, but it's not quite 5. So in words, what this set means is it's all real numbers between 0 and 2, not including 0 nor 2, and all real numbers between 3 and 5, not including 3 nor 5. I guess that's how you would describe this set in words. That's quite verbose. That's that's too many words. That's why interval notation is convenient. It makes this set a little bit more compact. Okay, so remember, brackets are used whenever the endpoints are included. Parentheses are used when the endpoints are not included. Sometimes you'll see a union. That means you're gluing two sets together. And okay, let's see. We're going to use interval notation to describe domain and range. So the domain is the set of all possible x values. That a function can take on. And the range is the set of all possible y values that a function can take on. And so we're going to have sets of numbers, sets of real numbers. So we're going to definitely use interval notation to describe them. When reading a graph, we read the domain from left to right. So domain, you got to read from left to right. Range, you're going to have to read from bottom to top. So domain is your x values, read from left to right. Range is your y values, read from bottom to top. And well, the domain, we denote the domain as x's and the range as y's. Okay, let's practice a little bit with interval notation. Yeah. So in these little two exercises, they want us to, this is a set, this denotes a set of numbers. It's the set of all real numbers that are less than -4. So these are all the real numbers that are less than -4, not including -4. And what we gotta do is we gotta do three things. We gotta graph the set in a number line. We gotta write the set using set builder notation. And we gotta write the set using interval notation. Okay, so I'll help you with the first one. So 1, we gotta graph this in a number line. So I have my number line, I have 4 right there, and right now I'm dealing with, and I put an open circle at 4 because I am not including 4. And it's everything that's less than -4. So everything to the left of -4. So that's what the set looks visually. Now I gotta write down, this is a set of values, this is a set of numbers. I wanna use builder notation. So I'm gonna open up some curly brackets. And so the curly brackets is just a container. And now you gotta tell me what goes inside this container. Well, what we're gonna say is that the elements of the container are numbers. And well, in order to denote some number, I'm just gonna call it x. So x, so my set contains numbers x, and then there's this vertical line. So I guess we're gonna say here you can sort of think as numbers x, and then this vertical line right here, you should read that vertical line as such that. So you're giving me the elements are on the left. This vertical line right here, you should just kind of think about it as like, just think about it as such that. Literally just say such that. So numbers x such that the number x is less than -4. So that's what I'm going to write here. X is less than -4. And that is the set builder notation. That's how set builder notation works. You're telling me. So it's a set of numbers. The set is represented by the curly brackets. And then you gotta tell me what's inside the set. Well, it's x's, some numbers x, such that, that's the vertical line. And then you gotta give me the description of the numbers that are less than -4. Okay, and let's do the last part, the interval notation. The interval notation in this case is pretty straightforward. It's from -infinity to -4 with a parentheses. And if you think about these three forms of expressing this set of numbers, I would say that interval notation is definitely the more convenient form. Okay, pause the video, take a minute, try to express this other set of numbers. This set of numbers is the numbers that are bigger than or equal to 3 in these three forms: in a graphical form, in set builder notation, and in interval notation. Okay, let's express it graphically, this set. So right now, it's the values that are bigger than or equal to 3. I am going to use a closed dot. And since our numbers that are bigger than or equal to 3, it's going to be everything to the right here. Yeah. Now let's think about the set builder notation. Okay, so I have a set. The set is my curly brackets, and the elements are some numbers, some x's, and then you gotta tell me what is the description of the x's. Well, it's x's that are bigger than or equal to -3. And lastly, the interval notation. So with interval notation, we're going to say, so it's all the numbers that are bigger than or equal to 3. So bracket 3 to positive infinity with parentheses. Okay, so hopefully you've been exposed at some point to this interval notation and it's starting to ring a bell. And if not, it's still at least hopefully starting to ring a bell. We're going to use interval notation to describe domains and ranges. The set builder notation is not as important, but just be aware of it. And also, it helps out to look at the graphical representation just to sort of understand what's going on. Okay, let's get into some exercises here. What you want to do is you're given some functions, or actually these are just relations. They might not be functions. Remember, in order to determine if a graph is a function, you gotta think of the vertical line test. Some of these graphs do not pass the vertical line test, so they're not functions, but they still have domain and range. And what we want to do is we want to determine the domain and the range of the following graphs, and we want to use interval notation. So let's see. Let's begin with the first 6. The first 6 graphs. Take a second, pause the video, try to determine the domains and ranges of all of these first 6 graphs. Okay, let's look at the first one over here. This top one over here, this wavy kind of trigonometric sinusoidal looking thing. What's the domain? So remember, to determine the domain, we're thinking about the x values, and we read the domain from left to right. How far to the left does my graph go? How far to the right does my graph go? Yeah? And notice that a lot of these little graphs have these little arrows at the end. There's this little arrow at the end of the graph. And what that arrow kind of indicates is that this pattern sort of keeps on going. Yeah? This pattern sort of keeps on going forever, either to the left or to the right or up or down or whatever. So how far to the left does this graph go? I mean, I see that this little arrow is indicating that this pattern sort of keeps on going. This little wavy thing just keeps on going forever to the left and forever to the right. So I am going to go ahead and conclude that my domain for this guy is from -infinity to +infinity. Yeah? Now let me think about the range. So the range is the y values. And you gotta think, how far down does my graph go to how far up does my graph go? So how far down does this graph go on the y? I think it goes as far down as -3. So from -3, how far up does it go? It goes all the way to +3. And are -3 and 3 included? Well, let's see. I mean, if they were not included, we would have little open circles over here at -3. We would have open circles at 3. But we do not have open circles. We just have a solid line, which means that they are included. So I'm going to be using brackets. So I am going to conclude that the range for this particular function is from -3 to 3 with brackets. Okay? So remember, the domain, you read it from left to right. The range, you read it from bottom to top. Okay, let's see. Let's think about the next one. Let's think about this one to the right. Let's first try to determine what the domain is. What is the domain here? How far to the left does my graph go? How far to the right does my graph go? And remember, these little arrows over here are indicating the behavior of my graph in the long term. So this graph just keeps on going sort of slightly down forever and ever. and it keeps on going and to the right forever and ever. So how far to the left does it go? How far to the right does it go? Would you agree that it goes to the left all the way to negative infinity, because this is going down, but at the same time it's slightly going to the left and down and left and down and left and down and left forever and ever and ever. So this just keeps on going forever to the left and also forever to the right. So I am going to conclude that the domain here is negative infinity to positive infinity. What about the range? How far down does my graph go? How far up does my graph go? Well, it keeps on going down forever, it keeps on going up forever, and well, then I guess we're going to have to conclude that negative infinity to positive infinity is also the range. So hopefully we agree on that. Alright, third example. Let's think about the domain here. What's the domain? How far to the left does my graph go? How far to the right does my graph go? It looks like my graph goes only as far as -4 to the left. And it is included. I see a solid dot right there. So that tells me that there's a bracket going on. So -4. How far to the right does my graph go? Well, according to this arrow, this behavior just keeps on going forever and ever and ever. So positive infinity is what I'm going to conclude. Now let's think range. How far down does my graph go? How far up does my graph go on the y-axis? Well, it looks like my graph goes as far down as my y value of 0 right there on the x-axis. And it is included. It is part of the range. So I'm going to say 0. How far up does the graph go? Well, according to this little illustration, this graph just keeps on going up forever. So 0 to positive infinity is what I'm going to conclude that the range is for this graph. Good. So far, we've only been dealing with functions. This graph up here passes the vertical line test. This one passes the vertical line test. This passes the vertical line test. These are all functions. We could call them f of x or g of x or something like that. This next one is not a function. It fails the vertical line test. And that's okay. It still has a domain and it still has a range. So let's determine its domain. How far to the left? How far to the right? That's what we're thinking when we're dealing with domain. So how far to the left does this graph go? Well, according to these arrows, this graph keeps on going forever to the left. So I'm going to go ahead and say negative infinity to how far to the right does my graph go? My graph goes as far as 4 on the right. So 4. And it is included. It is part of the graph. It's a solid dot. So 4. So I'm going to use a bracket. What about my range? How far down does my graph go? How far up does my graph go? And if you think about it, this graph sort of keeps on going towards the bottom left, and you know this behavior keeps on happening. So it keeps on going down and down and down and down and to the left. But it also keeps on going up and up and up and up and to the left. So I am going to conclude that the range is everything, negative infinity to positive infinity. And remember that negative infinity and positive infinity always require parentheses. Okay, so hopefully so far we agree on these domains and these ranges. Let's look at the next couple of them, few of them. What about the domain of this graph right here? How far to the left does it go? How far to the right does it go? It looks like it keeps on going forever to the left. It's just getting closer and closer and closer to the x-axis from underneath if I keep on going to the left. And it looks like it's getting closer and closer and closer to the x-axis, but from above if I keep on going to the right. Except right here at 2. When my x value is 2, my graph sort of broke apart. So how do you describe the domain? It looks like the domain is from negative infinity to 2, and then from 2 to positive infinity. But at 2, there is no value of my graph. So how do you describe that? Well, we're definitely going to have to use union, that little u. We're going to have to say the following. negative infinity to 2, and then union, and then 2 to positive infinity. But now I gotta think, should I use a bracket or a parenthesis at 2? Is 2 included in my graph? Is if my x is 2, so remember, if my x happened to be 2, they actually gave us the function right here. If my x happened to be 2, my denominator would be 0, it would be undefined. So yeah, we cannot really include 2 in our domain. We have to use parentheses. Yeah, that's the domain. What about the range of this function? So now think, how far down does my graph go? How far up does my graph go? Well, it keeps on going down forever, it looks like. It keeps on going up forever, it looks like, except that right there on the x-axis, my graph sort of broke apart. And well, the x-axis corresponds to the y value 0. So something similar to the domain happened, is just that now in the range, what we have is this. My graph is going down all the way from negative infinity all the way to 0, but I'm not really ever touching 0. And then from 0, I'm going towards positive infinity. So let's describe that range in the following manner. Negative infinity to 0. I never touch 0. That's why I have to include, that's why I have to use a parenthesis. Union 0 to positive infinity. That's how I would describe the domain and the range of this function. Hopefully that one is clear. That one's a little tricky. The next one. This one's a little bit more straightforward. How far down, how far to the left, how far to the, so how far to the left, how far to the right? Well, forever to the left, forever to the right. So negative infinity to positive infinity. What about the range? How far down, how far up? This thing just keeps on going down and down and down and up and up and up. So same thing. Good. Let's think about the last two. So far we've used pretty much, let's think about the last two. What's the domain of this function? And notice, right now we do not have these little arrows that we had before. Now we have these solid dots. What that is saying is that my graph stops at -2 and my graph stops at 4. So then I think for the domain of this one, the domain has to be -2, using a bracket. Why? Because -2 is included, that's why there's a solid dot, all the way to 4. That's what I'm going to conclude the domain is. What about the range of this function? I would say that the domain, so how far down, how far up does it go? Let's see, it looks like right now I'm thinking the y-axis. How far down, how far up? It went down as far as here, so that looks like -1. And it goes up all the way to pretty much just right there. I'm gonna call that 3. So it looks like the range is from -1 to about 3. And again, I'm just making up the 3. I don't know. I mean, they didn't give us what the value there is. It could have been 2.75. I don't know. I'm just gonna say it's 3. So, and again, it's using brackets. So -1 to 3. Yeah, so that's how far down my graph went, as far down as -1 and all the way to +3. Let's think about the next one. What's the domain here? Okay, well, it looks like the domain, how far to the left, how far to the right. Sorry, this picture is a little fuzzy, but we'll be okay. So this is my x-axis, and it looks like my graph goes as far to the left as -3 and all the way to the right as 4. And notice that over here I have a solid dot, and over here I have an open dot. The solid dot means that I'm using a bracket. The open dot means that I'm using a parenthesis. So I'm gonna say -3 with a bracket all the way to 4 with a parenthesis. What about the range? How far down, how far up does my graph go? I'm looking at the y-axis, and it looks like my graph goes down all the way to -3 and all the way up to 3. Sorry, 2. So -3 all the way to 2. and so -3 with a bracket, and all the way to 2, and also with a bracket, because that point is included. Okay. So definitely worth your time to master this ability of determining domain and range just based on a graph. Okay, let's move on. So let's think about what are called rational functions, functions that are fractions. Yeah, if you are given a function that has the variable x in the denominator, so if the x is in the denominator, you definitely want to avoid dividing by 0. So what they tell us here is that fractions with x in the denominator, to find the domain, you set the denominator equal to 0 and solve for x. The value that you find makes the denominator undefined and is not in the domain. Yeah, so let's see. Let's find the domain of this function f of x and express the domain using interval notation. Okay, so what we were told is that we should set the denominator equal to 0. Okay, and then we solve for x. So then that means subtract 8, divide by -4, so x equals positive 2. So this value is not in domain. Yeah, because if my x happens to be equal to 2 and I plug it into this function, it's going to make my denominator 0, and that's going to give you a y value that's undefined, which makes no sense. So we want to avoid the value 2. So then the domain becomes all real numbers except 2. And if you think about it, graphically that looks like this. So it's everything except for 2. It's everything to the left of 2 and everything to the right of 2. Yeah? How do we express that using interval notation? Well, it would be -infinity to 2, but I have to use a parenthesis with the 2 because it's not included, union, and then 2 to positive infinity. So hopefully that's okay. So anytime that you're dealing with a rational function is going to be some function that it's a fraction, and the denominator will have the variable x. If you're dealing with a rational function, you're going to have to set the denominator equal to 0, solve for x, and whatever values of x that you end up, you need to exclude them from the domain. You need to, those values of x are invalid. They're not part of your domain. You need to get rid of them. And all the other numbers that remain is your domain. Okay, next thing, next type of function, square roots, square root functions. So if I have a square root and I have an x inside it, in order to find the domain, what we're going to have to do is we're going to have to set the expression that's inside of the square root to bigger than or equal to 0, then solve for x. So according to these rules here, what we're going to have to do is the following. So I want to find the domain of this function. So what I'm going to have to do is I'm going to, and by the way, there are other ways of doing this. This is just one of them. We're going to say x minus 6 is bigger than or equal to 0. And anytime that you're dealing with inequalities and you're going to solve for x using an inequality, they tell us, remember, if you multiply or divide by a negative number, the direction of my inequality sign is going to flip. So if you multiply by -1 or divide by -3 or something like that, the inequality sign flips. So keep that in mind. So right now I'm going to solve for x. So to solve for x, I need to add 6. Well, that's okay. That doesn't do anything. It doesn't flip my inequality. It's only when I multiply or divide by -1. So x is bigger than or equal to 6. And that is my domain. That is the domain. So then I guess that's my domain. Okay, and the interval notation that corresponds to that is bracket 6 to positive infinity. Bracket, because I'm dealing with this type of inequality that allows for equal signs. So 6 is okay. If my x is equal to 6, then I have the square root of 6 minus 6, which is 0, and the square root of 0 is 0, so no problem there. Okay, so be aware of these two types of functions. Be aware of these two types of functions. You have what are called rational functions, the ones that have a denominator, and the variable x is in the denominator. To determine the domain there, what you're going to want to do is set the denominator equal to 0, solve for x, and then those values of x that you find, you're going to have to exclude them. You don't want those values, and then your domain is everything except for those values. If you're dealing with a square root function, what you're gonna have to do is set the inside part of the square root to bigger than or equal to 0, solve for x, keeping in mind to remember that when you multiply or divide by a negative, it changes the inequality, and whatever your answer is, that's the domain. Okay, so let's see. Let's determine the domain and the range of some more functions here. And we're going to use a little bit of the graphing calculator. I'll show you how to put these things into our graphing calculator so we can see the graph. Sometimes it's a lot easier to determine the domain and range of functions when you see the graph rather than just having an equation. So let me get my calculator here and show you. Okay, so let me look at question A. Yeah, I want to determine the domain and the range of this function. So I have my TI-84 right here. I'm going to enter this function into my graphing utility in my calculator. So let me turn on my calculator. I'm gonna clear this, well, it doesn't matter. What you're gonna wanna go to is, you see this right here, this y equals. So I'm gonna click y equals. And remember, f of x is just y. So right now, I'm gonna go to y1. y1, I'm gonna say equals x cubed minus 7. So x is right here, that's my variable, x, and then cubed, x cubed, the cube part, I'm gonna do to the, so there's this little caret, little symbol here, to the third, and then I don't want to keep on writing in the exponent, so I have to get off from the exponent. So I'm gonna click on my cursor here, to the right, see how it came down, and then I'm gonna say minus 7. So all I did is enter my function. I'm gonna go to graph. See, graph is right here because I want to see the graph so that I can see what the domain and the range is. So graph. Okay, that's right now my function got graphed on this little window. The window goes from -10 to 10 on the x-axis and from -10 to 10 on the y-axis. And this behavior, believe it or not, if you were to zoom out, which we can, you see we can zoom out. How do we zoom out? X. Whatever, it doesn't matter. So if we were to zoom out, this graph this behavior, so there's a little like bend right there, and then this branch just keeps on going down and down and down and down. And then there's this little bend, and my graph just keeps on going up and up and up. So based on that, I'm going to go ahead and conclude that the domain of this function, so how far to the left does it go? How far to the right does it go? Well, it keeps on going down, but towards the left, and this keeps on going up and towards the right. So I'm going to conclude that the domain here is -infinity to positive infinity. What about the range? How far down, how far up? Well, the graph keeps on going down forever down, and it goes forever up. So I think the range is the same. Okay. So that's using my calculator to figure these things out. Let me see. Let me use my calculator to enter this function right here. So this is the absolute value of x plus 3. How do I use my calculator? How do I use my calculator to see what the graph of this thing looks like? Well, in the same way. What I'm going to do is I'm going to clear the previous function that I entered. Alright, and now I got to enter absolute value of x plus 3. Well, where in my calculator is absolute value? So where in my calculator is absolute value? If you go to math right here, there's this button that says math. I'm going to click there. So let me just start from scratch. So I'm going to go to y equals. So I went to y equals up here. And I want to enter square root of x, absolute value of x plus 3. So where do I find absolute value of x in my calculator? So there's a button called math over here. I'm going to click there. And then you have math, num, complex, probability. I'm going to go to num, number. So I need to scroll to the right. And you see the first option says abs, and then there's a parentheses. Yeah, that's what I want. That's what I want. So I'm going to hit enter on there. See, I have my little absolute value. And then I need to put x in there. And we said that the x's were this number right here. So absolute value of x. Then I could write other things here, like absolute value of x, whatever. But right now, it's only the x that's inside the absolute value. So now I want to get out of the absolute value. To get out of the absolute value, I'm going to click my right little cursor here. Okay, so plus 3. And then I'm going to look at the graph. And that's what the graph looks like. Let's think about the domain. How far to the left does it go? How far to the right does it go? And this behavior just keeps on repeating. So my graph goes forever to the left, up that way. My graph goes forever to the right, up this way. So I'm going to conclude that the domain is from negative infinity all the way to positive infinity. Domain, negative infinity, positive infinity. What about the range? What about the range? Let me look at my graph again. How far down does my graph go? How far up does my graph go? Well, it looks like my graph goes down as far as 3. Y equals 3. So 1, 2, 3. As far as 3. And it keeps on going up forever. And 3 is included in my graph. Otherwise, there would be like a little gap there. So I'm going to conclude that my range is from 3 to positive infinity. Okay, so hopefully that's okay. Also, if you just know about these graphs before, then you just know that this is a cubic that's been shifted down 7 units. This is the absolute value function shifted up 3 units. And so you might be able to look at the graphs just by memory and a little bit of deduction. All right, so let's think about these next exercises here. We want to determine the domain only. We don't care about the range right now. We want to determine the domain. And we could do these problems by entering the function into my calculator and looking at the graph. But let's try to do them without the usage of a calculator. Let's just try to do them by what we know at this point. Okay, so what we're going to do here is, let me look at the easier one first, part D. I want to determine the domain of this function. And remember, this is a function it's a rational function. It has x's in the denominator. So what we said earlier is that if you're dealing with a rational function and you want to determine the domain, you set the denominator equal to 0 and solve. So let me begin with that. Okay, now let's solve this. How do I solve this equation? How do I solve this equation? Well, this is a little skill that hopefully you have available to you, and it's by factoring. We could use factoring. We could also use what's called the quadratic formula. There's this little thing called the quadratic formula. So let me just there's some techniques here. So factoring, quadratic formula. Remember, the quadratic formula says this, that ax squared plus bx plus c equals 0. The solutions are going to be given by negative b plus or minus square root of b squared minus 4ac over 2a. Yeah? If you want to go that route, sure. I think factoring is a little bit easier here. What we could do is the following. What we kind of want to do here is we want to rewrite this trinomial. It's a trinomial because it's a polynomial with 3 terms as a multiplication. So something like this. So something times something should give me x squared. Well, that's going to have to be x and x. We're thinking about FOIL backwards right now. So x times x is going to be x squared. And then something here times something there should multiply to 5. It should multiply to positive 5. And not only that, but also add up to negative 6. So can you think of 2 numbers that multiply to positive 5, but then if you add up those numbers, they end up with negative 6? Well, then I'm gonna kind of think that this is negative 1 and minus 5. And let's see if this works out. X times x, that's x squared, so that's good. And then x times negative 5, well, that's negative 5x. Negative 1 times x, that's negative x. So that negative 5x and negative x gives me negative 6x, so that's good. And negative 1 times negative 5 gives me positive 5. And now, what I have to do is set each one of my factors equal to 0. So x equals, this is not 0. X equals 1 and x equals 5 because I had to add a 1 and I had to add a 5. So right now I have found the values that make the denominator, the x values that make the denominator 0. So we do not want those. So then the domain is going to be everything except for these x values. So let's see if we can visualize the domain first graphically. So this is 1 right here. And this is 5. And I do not want 1 and I do not want 5. And my domain is, well, pretty much everything else. All the numbers that are less than 1, all the numbers between 1 and 5, and all the numbers that are bigger than 5. That is my domain. It's everything except for 1 and 5. So how do we describe that using interval notation? I think I would describe it like this. Negative infinity to 1, parentheses, union 1 to 5, and then union 5 to infinity. That's what I would conclude is the domain for this function. Okay, let's think about the next one. You should pause the video and see if you can do this one on your own. So let's see. What we want to avoid here, is, we have kind of a double whammy right now. We have a rational function, there's x's in my denominator, and there's also a square root in the denominator. So right now, what we're going to have to do is, earlier we said, there was an example up here that we did. What we did is we set the inside part of the square root to bigger than or equal to 0. Well, right now I do not want the equal to 0 part, because if it's equal to 0, I'm going to be dividing by 0. So right now I'm going to have to use a strict inequality. I'm going to have to say 3 minus x is strictly bigger than 0. You see, I don't want the equal part down here because I don't want this thing to be equal to 0, because otherwise my denominator will be 0. Okay, so now let's solve for x. Okay, so I'm going to subtract 3 from both sides, so that looks like this. Negative x is bigger than negative 3. And now I want to solve for x. So how do I get rid of this negative right here? I'm going to multiply both sides by negative 1. But remember, if you multiply both sides of an inequality by a negative, that flips the inequality sign. So if I multiply both sides by -1, this will become positive, but my inequality changed. So x is less than 3. So everything less than 3. So then here my domain is going to end up being all the numbers that are less than 3. So that's from -infinity to 3 with a parenthesis. That one's tricky. That one's a little bit tricky. We do not want the denominator to be 0, and we do not want the inside of the radical to be negative. That's what we're trying to avoid there. Okay, so hopefully you agree with this. Let's move on to the last example in this part. All right, so they gave us a little prompt here. They're telling us that in the year 2014, $23.63 was equal in value to $1 in 1913. In the year 2000, $17.39 was equivalent to $1 in 1913. Well, I wish I had many dollars in 1913. Let's see. So they tell us the amount it takes to equal the value of $1 in 1913 can be estimated by the linear function v given by, so they give us a little function. Let's understand this function. X, so the x is the input, is the number of years since 1985. So v of 10, so 10, that would be, v of 10 gives us the amount it took in 1995 to equal the value of $1 in 1913. Yeah? So let's see if we can answer these last little parts here. The first part asks us to use the function to predict the amount that it will take in 2018 and 2025 to equal the value of $1 in 1913. The second part asks us when will it approximately take $32 to equal the value of $1 in 1913. If I was you, I would pause the video right now and see if I could just take on the challenge, see if you can answer these two little parts. Okay, let's see. Let me help you answer them then. So let's see. I want to use the function to predict the amount that it will take in 2018. So let me first think of the year 2018. So the year 2018, that corresponds to, so remember, the value x, the input for this function, is the number of years since 1985. So how many years, so what's x? So if the year is 2018, how many years since 1985 is that? So let's see. I guess what we could do is just 2018 minus 1985. That's 33 years. Yeah, so x equals 33. Because 1995, that's 10 years. 2005, that's 20 years. 2015, that's 30 years. And then another 3, so 33. So right now what we gotta do is we gotta say v of 33. Okay, well that's going to be 0.436 4306 times 33 plus 11.0043. Let me use my calculator to help me out here. So we have, let me get out of here, so second quit. Let me clear this. 0.4306 times 33, enter, whatever that is, plus 11.0043. Okay, so that gives me 25 and about 21 cents. 25 and about 21 how much was it? 21 cents. So in the year 2018, $25.21 was the same as if you had had $1 in 1913. But then again, back in 1913, like a sandwich cost like a nickel, and you could probably buy a nice pair of shoes for like $3. So inflation is called. Okay, so hopefully this is okay. Let's think about the next one. 2025. What is the year 2020? What x corresponds to the year 2025? How many years since 1985 is 2025? I think that is going to be what, 40 years? That is definitely 40 years. Okay, so my x is 40. And right now what we gotta compute is v of 40. Okay, well, that's going to be 0.4306 times 40 plus 11.0043. Let's see what we get. Let's see what we get. My calculator. So now what we need to do is 0.4306 times 40, enter, plus 11.0043. And I get about $28. $28 and about 23 cents. I'm gonna round to the nearest cent. $28 and 23 cents. So hopefully this is okay. I think this last part is what's a little tricky. So when will it approximately take $32 to equal the value of $1 in 1983? So when, what year? So to set this up now, instead of plugging something into my function, what they've given us is the y value. Remember, the y value is the v of x. They've told us v of x is 32. Now find the x that corresponds to that. So we have to set it up like this. 32 equals 0.4306x plus 11.0043. And then we gotta solve for x. Okay, well, let's solve for x then. Let me begin by subtracting 11.0043. Okay, use my calculator. So we have 32 minus 11.0043. That gives me 20.9957. So 20.9957. And that is equal to 0.4306x. Okay, now I gotta divide everything by 0.4306. Divide by 0.4306. Okay, so let me use my calculator to finish this. So I have already the value 20.9957 right there on my calculator. I'm gonna say divided by 0.4306. Enter. And I get, it's almost 49, so 48.7. 48.7. And now we're talking about x, so I guess this means 48.7 years since 1985. What year is that? So 1985 plus 48.7 That's about the year 2033. 2033, whatever, almost 2034. Yeah. Okay. Thank you. Hopefully, these ideas are clear, and I'll see you in the next section.